So let's continue. I think one very good topic we have done, that is the definition of fluid, and in the definition of fluid some objective questions we have got. So now the question comes that with help of fluid mechanics you want to design devices like pumps, turbines. You want to design a system such that there is a reservoir in the city, it has good amount of water, but we want to supply water from that reservoir to the homes. So you want to lay down the pipe network, okay? So we know, right now we know that when we apply forces on a fluid, how it behaves. When we apply shear force on fluid, how it behaves, how it moves and deforms. So the question comes that if we have a problem, say we want to design the dam, we want to design the pump, or we want to design the turbine, what should be the methodology for solving that problem? What should be the methodology for deriving the formula? Okay, so suppose you are talking about pump. So what is pump? Pump takes in some water, adds energy to it and gives the water out, something like this, very basic simple language. Okay, so actually you want relationship between mass flow rate, pressure difference, that is force, and pumping power requirement, that is energy. So in almost all the problems, either you want to talk about mass flow rate, forces, that is pressure difference, or energy requirement, power requirement. Okay, you want to develop relationships between the three. So for any problem, you are going to write down three equations. That is mass conservation principle, Newton's second law of motion, and energy conservation principle. Okay, so let me give you just a very basic idea of how to solve a problem. So you can write down methodology. Okay, so I will take an example. Let us say construction of dam. So I think yesterday with you guys only I gave you an idea that you can say dam is a cantilever beam which is fixed at one end. Now since the left hand side of the dam is exposed to water, therefore at any point of the dam the water will apply some pressure, right? And when we move down in water, the pressure increases. So here the pressure is minimum, actually it will become zero. Later on in fluid statics you will call this pressure as zero, and at the bottom the pressure is maximum. So this is the pressure values, these are the pressure values on the dam surface. Okay, so basically this figure represents the distribution of pressure force. It represents the distribution of pressure force. Now what you want to do is you want to design the dam. So for designing the dam you need to find out the BMD and SFD. And for drawing BMD and SFD you need to find out the reaction moment and reaction force. But for predicting reaction moment and reaction force, first of all you need to find out the resultant of this pressure distribution. Resultant of this pressure distribution, right? Now the question is how to find out this pressure force. So what you will do is you will say that let us suppose there is a point on the surface and this point has area dA. This point has area dA. So what is the pressure over here? The pressure is P. So what will be the force at the point? The force at the point will be pressure into area, PdA. This is the force at a single point, okay? But like this point, there are so many points. At every point there will be some force. So when you will add all the forces, you will get the total pressure force on the surface. Am I right? What I have done is, I have taken a point which has area dA. At this point, pressure value is P. So force will be P into dA. So what is the pressure force at single point? It is PdA. But like this point, there is infinite number of points. Every point will have some force. So when you will add all the forces, you will get the total pressure force. Is that correct? Okay, now do one thing. Let us consider this point as the reference, and from the top surface of water, the depth of dA is h. What is the depth of dA? It is h. So I think what we are saying is, as we move down in water, pressure increases. Therefore, may I say pressure is a function of H? May I say pressure is a function of H? So I think in order to solve this integral, first of all, you need to understand what is pressure as a function of H. And what you will say, the very first point is at H equal to 0. The very last point is at H equal to capital H. So what you will do is, you will solve this integral from H equal to 0 to H equal to capital H. But for solving this, first of all, you need to find out pressure as a function of H coordinate. You need to find out pressure as a function of position, that is H. And how, and this is what our major problem is. Our major problem is not finding out FP. Our major problem is finding out pressure as a function of H coordinate. Once you know this, this is very easy to solve. So main problem of fluid mechanics is this: pressure as a function of position. Pressure as a function of position. Okay? So how you do it? So I think we are talking of forces, So for any problem, what you are going to do is, inside the fluid, you are going to take a fluid element. Okay? So say for example, this is air. So in the air, I will consider this particular air element, this particular mass of the air. Okay? Now this mass, it is going to have some weight. And this mass is surrounded by remaining air. So remaining air will apply some surface force on it. Okay? Is that correct? Is that correct? What I will do is, in the water, I will take a water element. Okay? Now this water element, it will first of all have some weight. But this water element is surrounded by remaining water. And the remaining water will apply surface force on it. But the surface force has two components. One is pressure and the other one is tau. Is that correct? But for dams, water is at rest. So if water is at rest, what will be the value of tau? Very good. The value of tau will be 0. So on the element, there is only weight and pressure. Right? On the weight, there is only, on the element, there is only weight and pressure forces. Now the fluid is at rest. Therefore, this element will also be at rest. So for this element, you will write down net pressure force on the element plus weight of the element will be equal to 0. This Newton's second law of motion I have written for the element. And when you will put all the terms, actually in the equation, you will get derivative of pressure with respect to H. Actually, this Newton's second law of motion will be a differential equation in form of dP by dH. So when you will solve this differential equation, you will get pressure as a function of H. Okay? So in any of the problem, what we are going to do is, we are going to take a fluid element. We will write down the forces for the fluid element, find out the forces for the fluid element, and then write down the Newton's second law of motion. Now this Newton's second law of motion will actually be a derivative in terms of pressure in terms of coordinate. So this is a differential equation actually. So when you will solve the differential equation, you will get pressure as a function of coordinates. Kumar, actually you are correct. The pressure will act on all the surfaces. Pressure will act on all the surfaces. Just for showing, I wrote it like this. I have written a net pressure force. Similarly, let me take one more example. Let us say the aeroplane is flying. You want to design an aeroplane. Suppose you want to design an aeroplane. So when we talk of aeroplane, let us say this is the Rafale fighter jet. The new fighter jet which India has bought from Dassault Systems, France. And aeroplane is initially on the ground only. So when aeroplane starts moving, with respect to the aeroplane, the air moves in the backward direction. Now, when we are talking of aeroplane, by the way, civil guys, this can be a skyscraper also. Okay? The idea is same, method is same. So suppose there is an aeroplane which has started moving in the forward direction. So with respect to aeroplane, the air will move in the backward direction. Okay? So some air will move over the upper body and some air will move over the bottom surface. Upper surface and bottom surface. Similarly, when a skyscraper is standing on the ground and the wind blows, the wind gets distributed. Some wind flows over here and some wind flows over here. When you are talking of skyscrapers now, understanding the wind is very important. Not only for structural analysis, but for business in the area also. ठीक है, कभी discuss करेंगे fluid statics में, fluid kinematics में discuss करेंगे that how the wind motion around the skyscraper affects the business of small shops like newspaper, food and everything. ठीक है? So air is moving like this. Now air and aeroplane, they are in contact, है ना? So there will be some surface force. So what air will do, it will apply pressure on each and every point of the aeroplane and similarly shear stress on each and every point. I hope the red color is visible, guys. Okay, now consider a single point. Okay, this point has area dA. At this point the pressure is P and at this point the shear stress is tau. Okay, so at the point, first of all, there will be a pressure force at the point and similarly there will be a shear force. These are the forces at a single point. So when you will integrate, you will get the total pressure force on the body. You will get the total pressure force on the body. And similarly when you will integrate, you will get the total shear force on the body. So if I want to use very basic language, actually I am going to be a little inaccurate now. This is not the correct situation which I am telling you. There is some difference, okay, but just for understanding. Now this pressure force, now for this pressure force, we call it as lift. And this shear force, you can call it as drag. So what happens is that when we are talking of aeroplanes or fighter jets, on these bodies, 4 forces are important. The first one is, below the wings of the aeroplane, there will be turbines. So what happens in the turbine? Turbine is like an engine. It pushes the exhaust gases in the backward direction. So because of that, there will be a thrust in the forward direction. So on the aeroplane, first of all, there is a thrust in the forward direction. Then there is a weight in the downward direction. And as the aeroplane moves ahead, the air applies some lift force on it in the upward direction and drag force on it in the opposite direction. Okay, who is applying lift? Air. Who is applying drag? Air. Now if the lift is greater than weight, the aeroplane will move up in the sky and this drag should be minimum so that the speed is high and fuel consumption is minimum. Is that right? Anna? If the lift is greater than weight, the aeroplane will move up in the sky, and if the drag force is minimum, the speed will be high, acceleration will be high, and fuel consumption will be minimum. So what is our purpose? We want to design the aeroplane in such a way that lift is greater than the weight, drag is minimum. Hana? So what you will do? You will take a basic design and you will try to find out when this basic design moves, what is the value of lift? What is the value of drag? Hana? And for calculating the lift, you need P. For calculating drag, you need tau. Hana? You need to find out pressure at each and every point. You need to find out tau at each and every point. So basically what you want to do is, you will use a coordinate system, let us say X, Y and Z. So this point will have some coordinates X, Y, Z. Point on the aeroplane. So you want to find out what is pressure at X, Y, Z. You want to find out what is shear stress at X, Y, Z. Then only you will be able to do this integration. So procedure is again the same as previous example. What I will do is, I will consider that there is a fluid element. And the fluid, basically air element. And the air element is moving like this. Now on the air element, first of all, there will be some weight. And secondly, on the air element, there will be some pressure forces. Now the air is moving. So tau will be 0 or non-zero? Now the air is moving. Tau will be 0 or non-zero? Non-zero. Very good. Tau will be non-zero. So here you will have some tau also. So on the fluid element, what you will say, there will be some net pressure force. There will be some net shear force, or you can call it as viscous force. Then there is some weight also. And since the element is moving, this net force is equal to mass into acceleration. Now actually this equation, this is Newton's second law of motion only. Newton's second law of motion for a fluid element. Okay. And we call it as Navier-Stokes equation. So civil guys, this is what you do when you model a skyscraper in a wind tunnel. Same procedure. It's the same procedure over there. So what we do, we write down the equation for a fluid element. This is known as Navier-Stokes equation. Now when you will write this equation properly, in this equation, there are derivatives of pressure with respect to x, y and z. And also there are derivatives of velocity with respect to x, y and z. So basically, when you will solve this equation, differential equation, you will get pressure as a function of x, y and z. Similarly, you will get u as a function of x, y and z. But what is du by dy? Du by dy is tau. So you will also get tau as a function of x, y and z. Now I think your problem is solved. Is that clear? So actually this is what we are going to do. Whether you are going to find out the pressure variation in atmosphere, whether you are going to develop the relationships in flow-through pipes, or you are going to derive Bernoulli's equation, you are going to derive boundary layer theorem, everywhere you are going to follow the same procedure. You will take a fluid element. For that fluid element, you will write down pressure force plus viscous force plus weight is equal to mass into acceleration. That equation will be a differential equation or a set of differential equation. You solve those differential equations, you will get pressure as a function of xyz, tau as a function of xyz. So this is what the methodology of fluid mechanics is. Every chapter except for one chapter, that is chapter number 3, fluid kinematics. All of you, is it clear? Okay. So this is what the methodology is. You are going to use 3 principles and mainly Newton's second law of motion, but apart from that there will be mass conservation principle as well as energy conservation principle. You multiply forces by distance, you will get the work, and work done is equal to change in kinetic energy, that is energy conservation principle. So whenever they are asking you pumping power or power generated in turbine, you have to use energy conservation principle. And since they will also ask you mass flow rate, so you will use mass conservation principle also. Okay, so you will write down any problem of fluid mechanics will be solved using 3 equations: mass conservation principle, Newton's second law of motion and energy conservation principle. Let me write it down. So methodology will be, we will use 3 equations, 3 principles: mass conservation principle, Newton's second law of motion, and the third one is energy conservation principle. Now what is mass conservation principle? Let us say there is a room or there is a packet of toffees. Inside that packet, initially there are 100 toffees, and I love chocolates. So what I did is, out of 100 chocolates, I took out 10 chocolates. But suddenly my wife came, so I have put back 9 chocolates. I fear her. She is very furious. She is always furious. So out of 100 I took 10 chocolates. Suddenly she came, so I put back 9 chocolates. So what you will say? Initially the number of chocolates was 100. I took out 10 and then I added back 9. So what is left inside? 99. So you can also say 99 minus 100 is equal to 10 is equal to 9 minus 10. You can also write like this. What is this? final mass minus initial mass is equal to incoming mass minus outgoing mass. Is that correct? So this is mathematical form of mass conservation principle. Final mass minus initial mass is equal to incoming mass minus outgoing mass. Or you can say change in mass of a control volume. Change in mass of a control volume is incoming minus outgoing. So same equation we will write down for flowing fluids also. So what we will say? Let us say this is the space where some fluid is flowing. Okay? And in this space, let us take a point. Around that point, there is a control volume. So in the control volume, some mass will come inside, some mass will go outside. So finally, when you will write the equation will appear something like this. Do not worry. I will explain this equation when we will derive it. We will derive it in chapter number 3. This is the mass conservation principle. This is the mass conservation principle at a point where the fluid is flowing. Okay. The left hand side represents incoming minus outgoing. The right hand side represents change in mass. Is this sufficient, all of you? कोई doubt तो नहीं आ रहा है? घबराने की जरूरत नहीं है. We are going to derive these equations in the chapter number 3. This equation I will derive in chapter number 3. This equation I will help you write down in chapter number 2 for fluids at rest and chapter number 4 for moving fluids. This equation also I will help you write down in chapter number 4. So Newton's second law of motion. So when you will write down Newton's second law of motion, final minus initial Saeed, final minus initial matlab change. Final length minus initial length, change in length. Final mass minus initial mass. Final toffees minus initial toffees is equal to change in number of toffees. है ना? So this is a control volume. Mass is coming inside, mass is going outside. So change in mass of control volume. I have to check the equation. I think it's correct. Is there any problem in it? I think it's correct. Grad dot rho v equal to del rho by del t. Oh, sorry. Now I got it. Along with the negative, this is incoming minus outgoing. Sorry, my mistake. Along with the negative, that is incoming minus outgoing. That's my mistake. Thank you. This means you are attentive. ठीक है. So similarly for Newton's second law of motion. So actually Newton's second law of motion, what we will do is we will take a fluid element. For that fluid element, we will write down pressure force plus viscous force plus weight is equal to mass into acceleration. Okay. Now this equation is known as Navier-Stokes equation. And you know what happens is that because of this term viscous forces, this equation is very complicated. So I will talk of ideal fluids. What kind of fluid? Ideal fluids. Ideal fluids means non-viscous fluids. Okay. So what we have is, I think I wrote down earlier that tau is directly proportional to du by dy. Right? So when you remove the proportionality sign, here you get a term dynamic viscosity. Okay. So ideal fluid is an hypothetical case which considers that the dynamic viscosity of the fluid is 0. But actually no such case like this is possible. Every fluid is going to have some viscosity. So just to make this equation simple, we are going to assume that the fluid is ideal. So if the fluid is ideal, whatever may be the value of du by dy, the tau is going to be 0 only. And if the tau is going to be 0, the viscous force will be 0. Okay, so such an equation is known as Euler's equation. Euler's equation means Newton's second law of motion for a fluid element considering the fluid to be non-viscous in nature. And ultimately this term is written as, this equation is written as, this is the Euler's equation. We will derive this equation in 4th chapter. And finally, when you multiply forces by distance, you get the work done. Work done is equal to change in kinetic energy. So you will get this. Okay. So these are the 3 equations which we are going to use in our fluid mechanics. The first one is mass conservation principle, the second one is Newton's second law of motion, and the third one is energy conservation principle. Now I hope you are able to see that in these equations we have some terms. One is pressure, the other one is density, similarly there is viscosity, there is velocity. So actually, while writing down these equations, there are two approaches to describe these properties. In fact, I should say in a different manner. I should say like this: when we are writing down these equations, there are two approaches to write them down. One approach is Eulerian approach, other one is Lagrangian approach. Okay, please listen to my statement. What I am saying is, when we are writing down these equations, there are two methods to do it. One is Eulerian approach and the other one is Lagrangian approach. So we need to understand what these approaches are. V is the velocity vector, magnitude of velocity, speed. Jyoti, V is the magnitude of velocity. V by 2, V square by 2. Derivative of V square by 2, it represents change in kinetic energy. V square. Okay, so there are two approaches to write down these equations. One is Eulerian approach, the other one is Lagrangian approach. And to understand these approaches, I will discuss with you how to solve the traffic problem of a city. Okay, this is what I am going to discuss with you.